Okay, so in chapter 7, we have been, or module 7, we've been talking about motion as we are moving through things. Okay, so beforehand, let's go back and look at it. We learned that there's gravity, right? Who knows the two different forms for our acceleration of gravity?
9.8 meters per second squared.
Okay.
32 feet per second squared.
Perfect. I'm glad you guys can read notes well.
I wasn't reading.
9.8 meters per second squared and 32 feet per second squared. So that is acceleration due to gravity. That is also a rate, in our formula that we've talked about for a couple of different modules now. Distance equals rate times time. Okay? So as far as we move something, it's going to be our rate times how long it's going to be falling, right? So you can either use meters per second or you can use feet per second squared. You need to know those two numbers. So if something is falling for 2 seconds, we're looking at 2 times, might be 64 feet per second squared, okay? So we dealt with gravity. We dealt with different types of friction. Just as a quick review. And so when we have motion, things that are opposing motion is friction. We have friction because every single surface has grooves that grab, just like Velcro. We talked about that, where they can grab on different surfaces. When the surfaces get smoother, there's less grab to them. Okay, so if I was driving on ice, why is that such a problem?
There's less friction.
Because it reduces friction. So typically, I have my tire. Does everyone look at your tires? Are tires smooth? If you have bald tires, whenever you need to replace your tires, it's also a problem. This is why they don't want you to drive on your tires that are baldy, because your tires are made like this, right? With those little grooves. And sometimes they even have like little extra grooves or grooves in the grooves of them. And then we have our bumpy road, and if it's Oklahoma, it's a very bumpy road, okay? So all of these different groove parts are grabbing on all the groove parts of the road. When there is ice, the ice has filled in all of these bumps and makes it smooth, or at least significantly smoother than the road was. So in comparison, we have less places for your tire to grab. Right? So you're going to slide. If your tire is really worn down and you hit the brakes, you're really going to slide. Right? So every time we are reducing those grooves, we reduce friction. Friction is a force that is always at play. We have friction from surfaces. We also have friction. Air causes friction. Fluids cause friction. We talked about fluid motion, which is like, so even if you dive into a pool, if you don't do force, you're not going to keep going forwards, right? So your fluid's going to cause friction against it. So we have lots of different friction, lots of different motions opposing our motion, okay? We also have what's called inertia. That was a word that popped up. Inertia is just an object's ability to resist change. So I like to just label it as resist change up there. So an object, the inertia that it has, inertia means like getting things moving is how it's often referred to. So if I have a small object, is it going to have a large inertia mass, or is it going to have small inertia if I have a small object? If I have a small object, its point of inertia is going to be small because it doesn't take much to get it moving. So just like whenever we had, remember before when we had the water bottle in the book, and I think Jonas and Ben blow on them, or someone blew on them. It takes less, so the water bottle was smaller and had less mass than the book did, okay? So it took less to move the water bottle than it does to move the book. In the same way, that's how inertia works. So the larger an object is, the more effort it takes to get it moving. Okay? So we've got friction forces at play, we've got inertia forces at play. We learned about kinetic and static friction. So static friction is what? Who remembers what static friction is? Yes, Dane?
Like just this book sitting still.
Yes.
What makes it not move?
So it's the force that resists the change in the first place. So it's static, it's being still. So it's resisting it in the first place. Kinetic friction is friction that's what? Sliding. So once it's already in motion, then we're having to overcome kinetic friction. Our total force, remember we talked about it, were all of the things that were applied. So if I am pushing on this table, we have some static friction initially, then we'd have to get it moving, and then there'd be the force that I'd be applying to it. So which one is greater? Is static friction greater or is kinetic friction greater? Static friction is greater. So if you're pushing a car, once you get it rolling, it doesn't take much to push it, right? But it's getting it moving in the first place. So that static friction is the greater one. So if I said two objects have friction forces, one has a force of 8 and one has a force of 15, and there's no labels there, what would be 8 and what would be 15 if we were dealing with static and kinetic?
8 would be kinetic.
8 would be the kinetic friction force. 15 would be the static friction force. Yes, so. So now that we know all of these different types of forces that we have, Isaac Newton said there are some rules to how these forces play together. Last week we looked at Sir Isaac Newton's first law of motion. And so rest or motion, so it says an object at rest wants to stay at rest, or an object in motion wants to stay in motion, right? So objects want to continue in the same state that they started in. And if they're going to change state, something has to affect it for that change to happen, right? So it's also called the law of inertia. I like to remember it because inertia looks like a Roman numeral 1 if you do a capital I. So the first law is inertia. It can also be called the law of inertia. Okay? And we were looking at, with our lab that we did, when we pulled out the card, when we pulled it out quickly, what happened to the quarter?
Drop straight down.
Yeah, it wanted to stay in the same place it was already in until gravity took over. We were rolling the marble around the 10, and whenever it came out of the 10, did it go in a curved path? Or from that point, it went straight forward. So it wanted to go in the same direction that it had been going, and it was no longer being acted upon by the edge of that pie plate. So the next one, the second law is unbalanced forces, is how I like to write it down. And so Isaac Newton said that if an object is acted on by one or more unbalanced forces, the net force is equal to the mass of the object times the resulting acceleration. Okay, that's kind of a big handful, or a mouthful there. But basically it's just saying the net force, or what we would end up with at the end, is equal to its original mass times the acceleration that you end up with at the end. Okay? And remember when we talked about net force, kind of like if you're fishing, you throw it out, you catch everything in the middle. So our net force is our total force. So we've got to look at friction forces. We've got to look at applied forces. All right? So acceleration always has to be in the same direction as the net force. Right? Because if you're talking about it actually moving, an object is moving. If I have my bottle and I am moving it across the table, my force has to be applied in the same direction that it's moving. Because if I want the bottle to move towards the wall and I'm applying my force towards the fireplace, is it going to move towards the wall? No. Okay? So the force is always going to apply in the direction of the motion for it there. What's neat about this is that the forces have to be unbalanced for motion to happen. Okay, so Caleb and Luke, come here. About the same things. I want you guys to stand and put your hands together. Lean forward, put your hands together, and push on each other's hands, okay? Now both of you take a step back. Okay? Okay, both of you take a step back again. And try to stay balanced. Okay? Can you take a step back again? Okay. Very good. Okay. All right, let's go to his toes. Okay, there we go. So sit down. So I would say that Luke and Caleb are close to the same mass, but they're not exactly the same mass. They're probably not the same weight. Their bodies aren't distributed the same. I know Caleb does some phenomenal taekwondo. So, right? So he probably has some skills I don't have in that. And so, but you saw as the guys were leaning on each other, there was not a lot of motion that was happening initially. The more that we spread them out, some more motion happened. But the further out that they were applying, what did you guys feel with your hands from the beginning to the end? Were you pushing harder on each other? Were your hands like pushing together harder? Okay. So the force that they were experiencing with their hands, they could tell you, we're pushing a lot harder on each other than before, but they weren't moving. Okay? And that's because of this second law. The motion has to be unbalanced. So we had Caleb pushing, we could say, towards negative, if this was a number plane, right? And Luke is pushing towards the positive. So until those forces were unbalanced, no motion was happening. So our net force for motion to happen means we have to have an unbalanced force. Something has to be greater than the other for it to overcome. Right? So for this one, an example, an automobile with a mass of 12,000 kilograms is accelerating at a rate of 3 meters per second forward. So we have motion. Motion is forward. That means our force is moving forward. It says, what is the net force acting on the automobile? Our force is always going to be our mass times our acceleration. We are ignoring friction in this one. So we're simply combining these two. 12,000 times 3 gives us 36,000 newtons. Remember, newtons is the rate of kilograms per meter per second squared. We can break that out into it, okay? So then another one, it says during a crash test, an airbag inflates to stop the dummy's forward motion. So we've had our car, he's moving forward, we have our little dummy, and the airbag stops him. So the car is going that way, the guy wanted to go that way, the airbag is pushing back the other direction. His mass is 75 kilograms. It says if the net force on the dummy is 825 newtons. So we're putting our force up here at 825 newtons towards the rear of the car. What is the dummy's deceleration? Should we use the term deceleration? It's really just acceleration in the opposite direction, okay? So it's his backwards acceleration, okay? So net force is 825. His mass is 775 kilograms. Okay, we know that force is mass times acceleration. So we could plug them in and put 825 equals 75 times A, right? Or you can rearrange it in the first place. So we rearranged in the first place the force divided by mass. So we have 11 meters per second squared in the backwards direction. Okay? So weight is dependent upon what?
Gravity.
The pull of gravity. Can we replace weight for a force? Yes, we can. We can say weight is simply a force. It's the force that
Gravity's
our body has on the ground of this planet, right? And so the amount of force that I am putting on this floor right now is dependent upon my mass times the acceleration of Earth, because I happen to be on Earth. So the force that I would apply to the ground on the moon is going to be different, because it would be my mass times the acceleration of gravity of the moon. So our weight is dependent upon mass and acceleration. If I want my weight to change, what can I change?
Your diet.
Change my diet, and that would change my mass. Okay? I could also change what else? I could change where I'm at. Right? So when we want our forces to change, we can change forces. We could even change our weight. We change our force by changing either of the two parts affected with it. So we can either change our mass. If we changed our mass, would it change the force? Would it change our weight? Yes. Or we could change our acceleration. That means I might go to the moon. I want to weigh less. Okay? So think about it in those two different things. Okay, so Newton's third law is the equal and opposite. We've all heard that for every action, there's an equal and opposite reaction. I had rules. I had special thingies today. Now it says they are equal in size and they are in opposite direction. So every force has an equal and opposite reaction. So if I am pushing down the ground is also pushing up on me. If I stand in quicksand, I'm still pushing down on the quicksand in the same force, right? Does the quicksand push back up on me in the same amount that the ground does? No. So what happens? You start sinking, okay? We end up having those unbalanced forces. Okay. So then it goes back. So all of these are working in tandem together. Usually at the same time, flowing back and forth. So initially, I might have this fidget spinner, okay? It doesn't want to move, okay? So we've got our first law of inertia. An object at rest is going to stay at rest unless acted on by another force, right? So initially, here's number one. I act on it with a force, unbalanced force, okay? So now it's going to move. So now it's going to stay in motion unless acted on by another force. Because of the cool way that they make fidget spinners, we've got very little forces acting on it. What are a couple of things that are acting on it?
Air.
Gravity, friction, air.
Gravity, friction, air. Yep. Okay. So I have my unbalanced force that is acting on it. And it says there's an equal and opposite reaction. So I pushed and it succumbed to that. But what also, if it says that I pushed on the fidget spinner also had to push back on me. So I felt it, right? When you push on something, it might not take a lot, but like you're feeling it, it's pushing back on your hand. Like if I'm pushing on this table, if I push long enough, what's gonna happen to my hand? I'm gonna have a little indentation in my hand, right? From pushing, because the table is also pushing back on me. So that's this third law of motion. For every action, there's an equal and opposite reaction. Oops. Wait. Okay, it says the action and reaction force pairs do not cancel out because they are exerted on different objects. So often, if we were in the way that that is talked about, so we have a ball, okay? So if we said, I have one force that's acting and pushing this ball, and I have another force that's coming back, we'd go, oh, well, those cancel out, right? But that's not really what's happening, because I have my force number 1 is acting on the ball, and my force number 2 is the ball is acting on me, okay? So our forces cancel out with those unbalanced when they're acting at the same surface. So the thing that happened between Luke and Caleb, when they are standing here, they were not moving because they were both acting on that point where their hands were touching. Okay, do you understand how that's, so there was no motion that was occurring. Their forces were canceling out because they were acting at the same point. When we're looking at our equal and opposite reactions for Newton's third law of motion, we're talking about acting on different items. Okay, let's see. So, I think that's this one. I'm gonna go over this one. Okay, so when we have a net force, so I have a couple of things written down. Our net force is always our total. Whenever I write it, you might, or even in your book, you might see it as just one F. F with a little subscript of T, meaning total force. You could also do subscript of N, okay? So our net force is our applied force and our friction force. You will see it with a minus sign, and that's important to remember to subtract those two, because our applied force is acting in a positive direction, and our frictional force is acting in the opposite direction, and we, with math, write that as one is going to be positive and one's going to be negative. And that gives us our different arrows versus like talking about our arrows, okay? So if I have an applied force of 20 newtons, okay? And I have an object with a mass of 15 kilograms, and my acceleration is 0.1 meters per second, initially, we would need to say, what is the total force? So if I know, sorry guys, I didn't realize it was on your table. If I say an object, a 15 kilogram object is moving with an acceleration of 0.1 meters per second squared, okay? So I've got something and it's moving, okay? Got this object and it's moving at 0.1 meters per second squared, okay? The total force is 1.5 newtons, okay? That's because it's actually moving. So we've got it here, and it's moving. So whenever we have a total acceleration for a mass, that will always give you your total force. So when you have problems on your test or in your study guide, and it's saying you have an object, it's moving at, 2 meters per second squared, or it's moving at 12 meters per second squared. We're talking about an object that's already in motion. It's been going, okay? So we have an unbalanced force already, and they're telling us that it's the force that's acting on it now is 1.5 newtons. That's what's keeping it going, right? But that's not all the forces that are there, okay? It's the total force that we see, but with this bottle, what else is acting on it? I've got friction here between the table that is causing it. So how much am I really having to push this bottle? So the bottle's moving at something, but I'm applying a force, the table's also applying a force. So we know how much the bottle is really moving. It's it's moving with 1.5 newtons, but how much am I applying and how much is the table, okay? Well, we know that I'm applying 20 newtons, so I'm having to apply 20 newtons of force. So how much is the table applying? So we go back to our total is our applied minus our friction. So our total here would be 1.5, so we're gonna plug that in the same place. My applied was 20 newtons. We don't know what friction is. We're gonna solve for our frictional force. My friction is negative here. Okay, in math, to change the sign, you have to change the side. So basically, we're gonna add it to both sides, or we're gonna change the side. So I'm gonna move frictional force on to the left side of the equal sign. I'm gonna move my 1.5 newtons to the right side. If I change signs, I change sides. So I would have 20 minus 1.5, which tells me that that table, now if that was that, would be applying 18.5 newtons, where? In an opposite direction, okay? So again, we have everything, first the bottle doesn't want to move, okay? So there's our inertia. I'm gonna apply an unbalanced force to it and make it move. Here's our number 2, okay? And then as I'm pushing on the bottle is also pushing back on me. As the bottle's pushing on the table's pushing back on it. Okay, we've got several equal and opposite forces that are at play. Okay, in this case, as it was moving, we had a force where my hand was touching the bottle. We also have the bottle and the table that are doing some opposite ones, okay? Let's see. So there are 4 different types of forces. You guys learned about electromagnetic. As you get into college, we call it E&M, electromagnetic. So we know that electricity, those opposite charges, cause things to be attracted, right? That's what we learned about in all of our chemistry classes. We know that magnets are opposite charges, and so it's causing things to be attracted. And if you have 2 magnets, they want to be attracted together, right? So you have an electrical magnetic force. It says it's got charges. It's only between things with charges, and it can either be attractive or repulsive. If you try to stick 2 magnets, 2 north poles, and magnets together, what's going to happen? Push away. There's no way to try to get them together, okay? And it's pretty strong. If I've got magnets, if you especially have anyone that had like earth magnets, ever played with those? They're like the really strong ones. They can hold, they've got some pretty good force to it, okay? Second, we've got nuclear forces. And that's because everything is made up of atoms, okay? And our atoms, the insides are all of the nucleus, right? We've got our protons and our neutrons all in here. So then we never thought about it. We know that our protons are positive and then our electrons were negative, right? So we knew that that's what kept that together and actually keeps the atom bound in one unit so that all of its protons and electrons don't fly all over the place because these are attracted. But we just learned that there's a magnetic force that repels like forces. So if I have 2 protons next to each other, why aren't they pushing away from each other?
Because of the force.
So we never thought about that. We're like, oh, well, we've got our nucleus. Our nucleus keeps our electrons connected because our nucleus is positive. Our electrons are negative. That keeps our whole atom together. So then that leads to the question, they're like, but if the nucleus is a whole bunch of positive things, why aren't they all repelling each other? So they don't repel because of nuclear forces, and there are 2 different kinds, strong and weak. Okay, that's all you need to know about that. What's interesting, it was really interesting when you read through it, that it talks about quarks. And they talked about being able to actually change protons into neutrons. But then if we changed a proton into a neutron, we would actually change what our element is, correct? Because our element is determined based upon what the proton count is in the first place. So we can actually make one element turn into a different element. They use the nuclear fission and nuclear fusion to split atoms. That's how we get nuclear bombs and all of that stuff, okay? And then we've got a weak nuclear force, and then we have our gravitational force. Gravitational is the weakest of all. You need to know that. Gravitational force says that every object has gravity. Every object exhibits a pull on something else. So I have my own universe of gravity. Like I have my own gravitational force. You have your own gravitational force. Our Earth does. It's just my gravity isn't enough to attract you because the gravitational force is pretty weak, okay? But as our objects get bigger, so for planets that are bigger, then their gravity is stronger whenever you have more mass. So remember, gravitational force depends on the mass that you have, and it is the weakest of all of them. Okay, we are going to move and do our lab that is going to address our equal and opposite reactions. Okay, make sure, bring your notebook, open to page 208 in your notebook. I believe that's right. Is it 252, whatever? Yep. I think it's 208. Yes. 208. We are going to do the UD Science one as our lab.